last lecture, we have seen how concrete strength is affected by various mix parameters. Now, this time we shall see what are the factors, test factors which affect the strength of concrete. Remember, when we talked about earlier for the in the introductory discussion on strength of concrete, we said both test parameters and the mix parameters govern the strength of concrete. So, this lecture will start with compressive strength, the factors those affect the compressive strength, measurements, namely end condition and capping of the specimen, size, shape and aspect ratio of the specimen, rate of loading, moisture condition, etc. Compressive strength, let us see how do we measure. We apply uniaxially load into the specimen. We are applying load only along this direction, and so reaction from the bottom plates comes from this side, and the compressive strength is measured at the P max, the load, maximum load it can carry before failure, divided by area of cross section of the specimen. Right. Now, this test is there are variation possible due to various test parameters, as we shall see one by one, various factors, the way you apply the load, size of the specimen length to height ratio, length to diameter ratio, rate of loading and several other factors. So, one has to standardize the test procedure, test procedure and compare for comparison of different results coming out from different mix. So, this is done as far as this variation in results, and therefore, we have standard test condition, and that specifies in IS 456. As far as Indian condition is concerned, this is specified in IS 516. So, test method, this test is described in IS 516, IS 516, right. Okay. So, test condition induces variation in results, and standard test conditions are given in IS 516. A second way of testing them is not to test cube, but this is also a test suggested in IS 516. You can test a part of the beam. Now, this beam, once it is tested in flexure, we will discuss this flexure test or tensile test for tensile strength later on, but once you have tested and failed. So, this is the failure plane where it has failed, the beam has failed under bending test, and the remaining portion you can utilize for testing for compression. So, you can see a load is applied on part of it. This is D, this length is D, this length is D, and this length is also D. So, in other words, it is a kind of this dimension is same D, D. So, all these dimensions are same, it is almost like a cube, So, you are testing this part of the beam for compression. So, this is also part of the standard test, but this is not very common. More common is the cube test, which you utilize for both quality control purposes and judging the potential of the mix, potential strength of the mix, that has gone into making of concrete. Right. So, first factor that affects, we shall see that end condition, end of the test specimen affects the strength. Now, first thing is that it should be truly plane. You are testing a cube, right, and this you apply load through this surfaces, This surface should be truly plane. Otherwise, what will happen? If you have some sort of undulation, the load will be applied there, and local stress concentration will be concentration will be there, because effective area contact area is reduced, and through this effective contact area then you are transferring the load to a larger portion. So, there will be stress concentration due to this undulation, or if it is not truly plane, then contact area being less, there will be stress concentration, and this will induce reduction in the result. So, you will get apparently lower strength, if it is not plane. So, it has to be plane. Now, in case of cube, what we do? We cast the cube in steel mold. 5 surfaces are in contact with the steel mold. One top surface, we cast like this, with this surface, all surfaces, this surface, this surface, this surface, and this surfaces parallel to the screen are also finished, also in contact with the mold. This top surface is the finished surface, and which will normally have some sort of undulation. So, what we do? While testing, we test such that this is facing the person testing. In other words, this you should be able to see, the load will not come onto the surface, finished surface. So, this is what we do in case of cube. Of course, in case of cylinders, we cast it in this manner, cylinder we cast it vertically. So, load is also applied onto the finished surface. So, sometimes capping may be necessary, you might put capping in order to take care of the variation due to the non-planarity of the surfaces, but even otherwise people have seen during research what happens if you put some sort of capping material. Now, this helps us in understanding the behavior, also standardizing our specimen, right. So, that is what it is, right. So, therefore, what we have seen, surfaces cast against steel mold are smooth and does not require capping. Capping results in strength variation, that is what we are going to see now. The difference is attributed to lateral expansion of the capping material and concrete. Okay. We shall see that. If you have your specimen like this, and you have put a capping material, let us say at the top, some sort of capping material at the top and also at the bottom. Now, when you are applying load like this, due to Poisson's effect, there will be transverse movement of all this, transverse movement due to Poisson's effect. So, this will have a tendency to move. So, you have applied actually P load here, P reaction will come from there, but there will be transverse movement. Now, this material, the capping material here, see relative movement between this capping material and concrete, right, relative movement. If this movement of the concrete is restrained, if it is stopped, if it is somewhat restricted by this capping material, it will have some sort of effect, and if it is not restrained or restricted by this capping material, it will have a different effect. The effect is something like this. If you are applying a load from the other direction, then this is a situation of what is known as biaxial condition, and in a biaxial condition, apparent strength would be higher, in a biaxial condition, apparent strength would be higher. Okay, this we shall see. So, the difference is, that is why the difference is attributed to lateral expansion of the capping material and concrete. Okay, we can see this, what happens. Now, this is the results of several test specimen. For example, one is sulfur, one is alumina cement. So, this is alumina cement. Now, y axis is relative strength. If we consider this as the strength for strong concrete, 100, whatever alumina cement gives, you have done capping with alumina cement. That means, we had specimen, cylindrical specimen of this something like this, which looked like this, and we have done a capping here and we did capping here. If we do capping here, so after capping the loads were applied, from both these directions, So, when you put alumina cement, the strength that we get, we call it 100%. Now, let us look at strong cement, strong concrete. You will find that gypsum plaster shows lower strength than alumina and so on. Similarly, 8 is plaster of Paris with OPC, plaster of Paris pure and sulfur, and sulfur with some filler, sulfur with another filler, gypsum plaster, different combination, different mix might be, this is also gypsum plaster. So, you can say in strong concrete the variation is significant, there is large amount of variation. In case of a material, in strong, alumina, if it gives 100, then others something else, plaster of Paris with OPC gives much lower, whereas in weak concrete this effective relatively less, the effect of the capping is relatively less. Okay. We shall see why does it happen, we will understand this as we go through the next slide. Right. Now, what happens? This depends upon nu by E. What is nu? Nu is the Poisson's ratio, this is Poisson's ratio. This is E is elastic modulus, So, Poisson's ratio and elastic modulus. Now, what does it means? If I have high Poisson's ratio, then it will move laterally more, the stress induced along the lateral direction will be more, divided by modulus of elasticity, the strain along the lateral direction. So, this is a measure of the strain along the lateral direction. Now, if I have a material, the capping material which has got high nu over E, then therefore, it will move more, and therefore, it will restrain the concrete less, it will restrict the movement of the concrete less. So, higher Poisson's ratio to modulus of elasticity will restrict the concrete less, and therefore, the strength will be lower. On the other hand, if I have lower modulus of nu by Poisson's ratio to modulus of elasticity of the capping material, then this will then this will do what? If I have lower value of this will be stiff, it will not move in the transverse direction and it will not allow concrete to move, it will actually induce higher restraint onto the lateral movement of concrete, thereby apparent strength will increase. So, let us see, softer and weak material has higher expansion and their lateral expansion is more than that of concrete, and as a result what do? This higher expansion increases lateral strain in concrete and crack parallel to the load grows rapidly, leading to failure under lower load. So, this value is higher, it would mean that concrete would fail under lower load, whereas if it is strong, if the capping material is strong, then this will result in higher strength of the concrete, because a strong capping material which has got low Poisson's ratio by E, stiffness is less, high E does not want to actually deform. So, high E, right, and also low value of Poisson's ratio does not transfer too much of stresses along the transverse direction. Such material would itself will not deform laterally too much, and it will actually oppose the because they are bonded together, and there is a through friction, there is nothing more, because you have applied a high load P through it, and frictional force is proportional to the normal force, we know. So, when you apply high force, the concrete cannot move, there is a kind of frictional force which will restrict frictional force between the capping material and concrete, and therefore, lateral movement of the concrete will be restrained if nu by E of the capping material is low. In other words, if it is strong, then it will result in higher strength of concrete, higher apparent strength of concrete. So, capping materials really affect the strength of concrete, apparent strength of concrete. High alumina cement therefore shows a low highest strength, which means that high alumina cement shows highest strength amongst the material that we have seen. Therefore, if we use high alumina as a capping material, it shows highest strength, which means that it is quite stiff, it has got low nu divided by E compared to all other materials like plaster of Paris, etc., and that is why this variation that we saw. So, capping materials really affects the apparent strength of concrete, this is one thing, but we need not apply capping all the time. So, what is why we are looking at capping material? We do use sometime capping material, but that gives us the understanding that the restraint, lateral restraint is an important aspect as far as strength of apparent strength, measured strength of concrete is concerned. Now, come to the no capping material, and come to the cube which is just been loaded under the steel platen. So, this is my concrete cube, this is my concrete cube, and this is my machine plates, this is my machine plates, this is my machine plates. So, through which I am applying the load, through which I am applying the load. So, they have machine plates. Now, these plates themselves are usually steel, and these plates affect the produces the same effect as the strong capping material, right. So, this ones they produce the same effect as the strong capping material. It has got lower nu over E. So, it would actually have a tendency to increase the strength of the concrete, right. So, end platens themselves, the machine platens, the plates, because you will apply load through the machine hydraulically or whatever way it is. Now, these loads are applied through plates, some plates which actually applies the load, and this machine platen itself produces similar effect as the strong capping material. These plates restrict the movement and increases apparent strength. This plates restricts the movement and increases apparent strength. This degree of restraint depends upon the friction between the plates and the concrete surface. Higher the friction, restraint will be more, and of course, the friction itself is frictional force is function of the load itself, right. For very low restraint capping material, say wax, the difference is quite evident from the cracking pattern. Now, we shall see the cracking pattern which we have seen through a photograph few maybe 2 lectures earlier, 1 or 2 lectures earlier. If you remember, we have seen the failure pattern of the cube. Now, this becomes again apparent from the actually failure pattern observed in two types of capping. Like if I put a low restraint material, the crack comes vertically straight away, because I have applied load like this, and I have a low restraint. Low restraint means a soft, I have a low restraint, that means I have a soft capping material, right. So, it does not stop, it does not restrain the concrete from expanding along this direction, and therefore, the crack parallel to the direction of loading, as it should happen, because we have said the failure mechanism of concrete cubes are tensile failure along the transverse direction. So, this strain, it can reach early the ultimate strain, this can reach early, nothing is restricting, and throughout the specimen it can reach early the strain, and therefore, you see vertical crack and it fails at lower load. Whereas, if you have a high restraint, same loading, high restraint, now this is not being allowed, the restraint, this is not being allowed, because there is a force coming by from the platen, the force is coming by here, and since the material is connected, this material is continuous. So, this force here which is transmitted through this will be also transmitted through some other material. So, although you are applying load like this and the material is trying to bulge out in the transverse direction, this bulging is restrained. This bulging is restrained by a lateral force which acts at this point, the frictional force which acts at this point, and in turn actually it will not allow it to bulge out. So, failure strain would not be reached. In fact, there are several failure criteria for failure of concrete, stress criteria, etc., but the most well accepted criteria is the strain criteria, 100 to 200 microstrain criteria. That means, concrete fails when it reaches its ultimate strain, and accordingly therefore, when the ultimate strain is reached, in this case it will be reached early, in this case it will be reached late, and thereby you can see that the failure pattern is also different. And you remember, we showed you a photograph earlier of actual cubes, and these failure patterns were like this, right. But as you go away from this point, effect of this restraint reduces down, and therefore, you see the effect is practically it remains up to certain distance, this because frictional force is applied here only at these surfaces, this restraint frictional force is applied, which does not allow it to bulge out. Similarly, here only. So, this force gradually reduces down as you go from the surface of the cube to inner side, and that is why this pattern is something like this. This pattern is something like this. Okay, we will have more of it, more understanding of it further. Right. So, that is why we saw, you remember the photograph, and this is why we saw the failure of the cube was something like this. The cracks, you will see something of this kind, uniaxial cube, and you allow it to further crack, it will be something like this. You allow it to further crack, further grow the crack, and you will have something of this kind. Right. Now, this same effect of restrainment has some effect on the h by d ratio shape. So far I talked about cubes, and I also mentioned in one of the earlier lectures that in India and European countries we test cubes, but if you look at the North American or maybe Japanese or some other codes, they use actually cylinders. So, cylinders, even our code permits, IS 516 permits you to use cylinders, but this is not very conventional. Cylinder of length to diameter ratio, 2, that means length height is twice the diameter of the diameter. So, how h by d ratio affects the strength, apparent strength, that is what we are going to look into. In case of cube, this is equals to 1, in case of cube, this is equals to 1. Okay. So, shape of the specimen has got a role to play, right. All this idea puts us to the question that this is only cube or cylinder strength measurement, these are only relative measurements, as we shall see that h by d affects the strength of the concrete, apparent strength of the concrete. So, this only can be relative measure of strength potential of the mix and nothing else, as we shall finally conclude. So, let us see now restrictive effect of the plate is operative till a distance of 0.86 d from the end of the cylinder in case of cylinder of diameter d. Same thing will go if it is a prism, instead of a cylinder, if we are talking of a prism of square cross section, the same thing, similar, we can have similar sort of conclusion. Thus, h by d ratios, generally we adopt a fixed ratio of 2, h by d ratio of 2. But if you have different h by d ratio, same effect will be observed, similar effect will be observed, and this has been again attributed to same Platen effect, as we call it, the effect of the plate that we call as Platen effect. Strength results differs for specimen having h by d lower than 1.7. Remember, this cannot happen due to buckling, because buckling occurs at much higher h by d ratio. If you have done a course on design, RC design, then you would know that for length to side minimum dimension ratio of 12 and above, we consider it to be not a short column, but a long column. So, therefore, this is below only h by d greater than 5, you have buckling effect. So, there is no buckling effect in such dimension 1:2 or similar one we are considering, but strength result still differs from specimen having h by d lower than 1.7. This ratio decreases with increase in concrete strength as nu by E decreases. If I have a strong concrete, its nu will be lower, E will be higher, and although nu may not be much lower, but E will be definitely higher. So, nu by E decreases. So, if nu by E decreases, therefore, strength, apparent strength would be higher, as we have seen, and this effect also tends to nullify somewhat, because Platen and the concrete, their properties are nearly becoming similar. Okay, we shall see this effect. Let us look at the failure of cylinder. We have looked at the failure of cube. Failure of cylinder is something like this. Failure of cylinder is something like this. You see, initial cracks would be something of this kind. Then if you have applied load, now you can see there here again it is not vertical cracks, although cracks started vertically. At the center you have just vertical portion. In fact, in this portion you do not have any effect of the restrainment due to the plates. So, Platen effects is not there in this one. In this zone there is Platen effect, and one would see the crack formation of this kind, one would see the crack formation of this kind. Now, this is the experimental results of height to diameter ratio you see the strength, if you see the strength 13.8, H by D ratio, this is for H by D ratio of 2, strength is 13.8 MPa, this is 25.5 MPa and this is 51.7 MPa. Now, if I consider this as 1, 2, whatever I am getting at 2 as 1, you can see as I reduce down the H by D ratio, the apparent strength actually increases, apparent strength increases, the ratio increases. Why? Because the effect of restrainment, if you remember, we said it is up to certain height 0.86 D. So, if I reduce down, if this height is reduced, initially if this is 2, so restrainment would be there in some portion, right, up to this only 0.86 D. So, some portion 1 D, because there will be some internal portion where there will be no effect of restraint, and that is what we have seen in the previous sketch that we had shown earlier, because you had a central portion where something like this, and then the top portion something like this, and the bottom portion something like this. So, in a standard L by D ratio, H by D ratio 2 cylinder, you have some portion where there will be no effect of Platon effect, no Platon effect. But if I reduce down this height, some cases would be there where there will be superimposition of the Platon effect. For example, if it is 0.86 into 2, which would be 1.72. So, at 1.72, below 1.72 up to 1.72 onwards, there will be very little reduction in strength, but if you go lower and lower, Platon effect would restrict the transverse movement of the cylinder, resulting in increase in strength. So, when you go to 0.5, there is a significant increase in strength, and this effect tends to reduce when strength of concrete increases. The reason is because we said when the if I have a stronger material, it will have lower, this will have nu by E, this will have lower, this will have lower nu by E, because U would have increased. So, when you have lower nu by E, it won't, even otherwise it would not have moved, it would not have actually moved transversely, or its lateral movement itself wouldn't have moved much. So, the Platon effect would be somewhat diminished there. So, that is why you see it is much diminished, whereas in this case it is relatively high, it is relatively high, it is relatively high, it is relatively high. This was further confirmed by putting something like no packing, put 8 millimeter soft wall board, put 8 millimeter soft wall board like this one, and then when you have 2.4 millimeter plastic board, that is you don't have practically Platon effect, because it is plastics, so which is very soft, and it gave no effect of the H by D ratio. So, H by D ratio, the lowering of the strength, again this is due to Platon effect. So, we have seen that normal cube, cube shows a higher strength, or its failure pattern is like that, that is because of the Platon effect. And capping effect is translated into Platon effect, the plates which restricts, and if you put plates something in between, change the machine Platons by some softer material, you will find with soft material there is no effect of end restraint, there is no effect of end restraint. So, with less stiff packing, effect of H by D vanishes, as in the case of 2.4 millimeter plastic board. This aspect has been considered in various code, and therefore, say ASTM code or Indian code, it takes into account, it allows you to test cylinder for compression test, even Indian IS 500/416, but if you have a nothing less than 1 of course is allowed, you have to have 1:2. In special cases, normally we test cubes, sometimes we can test cylinder, but then cylinder H by D ratio is usually 2. If you are testing anything else, these are the conversion, this is the factors. Actually, for code test, in situ testing, this is sometime you have to adopt this, and these values are useful in such situations. So, you can see if I have 1 for this value, when this is the H by D ratio for H by D ratio equals to 2, H by D ratio is equals to 1, the correction factor is 0.91. So, this would show higher strength. So, that strength should be reduced by 0.9, since this shows higher strength, when H by D ratio is equals to 1, you have a strength which is higher than what you would have found here, multiply by a fraction in order to bring down to this. In other words, what is being said here is it would be about 10% higher, it would be nearly about 10% higher. This says, well, nearly same values, although slight variation, this is 0.91, this is 0.92, 0.89. So, the codes normally allow testing cylinders with H by D ratio 1 to 2, and these are the correction factor. This gives the least strength. As you go on increasing, there is an increase and there is an further increase. So, it is something like this, right. So, that is the effect of H by D ratio on strength. This same in a curve form as given in IS 516, it is like this, here the ratio of H by D and correction factors, which I mentioned for 2 H by D ratio equals to 2, this is equals to 1, for H by D ratio is equals to other values 1.0, this 0.19, etc., 89, etc. Similarly, ASTM C42 84A gives you this sort of, this is height by diameter ratio and this is relative strength. So, this is what it is. Now, cylinder to cube, there are two issues involved. One, of course, the volume it could be even different, but there is a difference. They are of course not of the same shape. There is a difference in shape. So, cylinder to cube, there is a variation in strength, because some countries do use cube and some other countries who use cylinders. So, the conversion is generally required at times, and this has been observed that compressive strength of cube, if you plot onto the x axis, and this is the compressive strength of cube in MPa and the corresponding cylinder strength. Now, you see this is the ratio, this is the depending upon the compressive strength itself, the ratio of cylinder to cube strength ratio would change, right. So, as the compressive strength increases, this ratio also changes, but it fits into a good straight line. Generally, what is done is we do not go into this kind of complexity, although this ratio is a function of the compressive strength, cube compressive strength of the concrete itself, but what we do is we generally do not go into this complexity. Instead, we use simply 0.8 as the ratio of cylinder to cube strength. So, what we assume is cylinder is about 80%, or cube strength is 25% more than that the cylinder strength. Now, this we are talking of the cylinder of L by D ratio equals to 2, H by D ratio equals to 2. So, cylinder of H by D ratio equals to 2, we take 0.8 as a multiplying factor for cube strength to get the cylinder strength, and if we want to do other round, increase the strength by 25%, multiply by 1.25 to get the cylinder strength. So, it is one of the issues of course H by D, but the shapes and also the volume of the concretes are different. So, both this put together makes it that it is about 0.8. So, that is what we have seen, the aspect ratio, how aspect ratio affect the strength of concrete, H by D ratio or end capping. Now, this end capping business of course is not very important in case of cube, but one thing has come to our understanding is that we should put that plane surface onto below the platen, right, and we also know why the shape of the specimen, the fractured shape of the specimen is as it is, why it is like that, what we have, like it is not a vertical crack, but the cracks are inclined up to certain point, and then you get again inclination in case of cubes, whereas cylinders you will have some vertical cracks at the center. So, nature of the cracks is also, nature of the fracture planes are also explained by this phenomena. But capping situations are more important when one looks into the core strength, in situ core strength. Supposing you want to find out the strength of the concrete in structure, then one has to do what is called core testing. You take out a cylindrical core, because we can easily drill cylindrical core, it is difficult to drill anything else. So, cylindrical cores are drilled and then they are tested, and there you might be using a capping, and effect of end capping is important there. Anyway, we will discuss this possibly sometime later on. So, at the moment let us see what are the other factors. The next factor that we are going to look into, size or dimension of the specimen. Well, one of the explanation given, there is a variation with the size of the specimen, as we shall see. The experimental results have shown there is variation, and one of the reasons that is given, attributed to the size, is that long cracks initiate fracture earlier, and in a larger specimen one is likely to find a longer crack, thus lower strength results. So, if the specimen size is larger and larger, it has not been really related to the aggregate size, but it has been related to the size of the cube itself. It has been observed that the higher cubes, larger size cubes shows smaller strength, lower strength, and it has been attributed to possibility of finding a larger crack in the bigger size specimen. There is something called size effect in fracture mechanics, but this may not be necessarily although it is similar, because in small size specimens it is not very easy to find the size effect, but some results have shown that larger specimen may likely to show somewhat smaller, lesser strength than smaller specimen. Experimental data of cylinder exhibit reduction in strength compared to 100 millimeter specimen for larger diameter, right. So, when you have diameter changes takes place, experimental data shown that there is a reduction in strength, and you have similar results for cube strengths also. Let us see how these strengths look like. You see, strength of the cylinder with the diameter is something like this. As you can see, as you go on increasing the size beyond 600 millimeter, of course, diameter, there is hardly any reduction in the strength, but before that there is a reduction in the strength. L by D ratio has been maintained 2 throughout. So, you have got diameter 600 and correspondingly the length, and you find that there is a reduction in the strength, but how much is the reduction? Okay, if this is for 200, if I call this is for 150 millimeter, actually is 1, the increase by lowering the diameter could be about 10%, even less than 10%, and increase and lowering of the results to increasing it to 600, the strength results could be as much as 15% lower. So, it is not a very significant lowering, but there is some lowering, and of course, you can think in terms of think it about that anything about 600 millimeter, 1 meter diameter concrete cylinder is usually impractical, but 200 or even 250 is possibly possible, but that is also not very practical unless you have large aggregate size, because usually the cube size should be at least 3 times larger than the maximum size of the aggregate, or cylinder size should be at least minimum size dimension of the cylinder should be at least 3 times more than the aggregate to make it representative. Otherwise, this is not representative of the mix that you have, because supposing you have 50 or 75 millimeter aggregate and you are taking a 50 millimeter core, then you will be leaving the large, it might be simply the aggregate alone, you might get all aggregate strength, and if you are making a cube, you will have to leave the large size large size aggregate, and you will be ignoring their effect. So, it is suggested that this minimum size of the specimen should be 3 times the size of the maximum size of the aggregate, and you can see the effect variation is about 10 to plus 10% to about minus 15%, or maybe 20, not even 20, somewhat lower than that. Let us say similar results in cube. Cubes, it has been observed that when you have cubes of the size 70 millimeter, you get 10% increase in strength, and 100 to 150, it was seen that there is no effect. So, you use 100 millimeter size cube or 150 millimeter size cube, it is same. Use 200, 5% reduction, 300 about 10% reduction. So, plus minus 10% variation due to size can be expected while testing concrete. So, normally that is why you have standardized this size, but it is many courts in the European courts, many European courts actually allow for testing different size of the cube, but you can compare a given size with the given size only. That means, one mix you make of 75 millimeter side length cube and another mix of 150 millimeter side length cube, that is not comparable. So, you can compare, after all they are meant for comparing the strength potential of a mix, and thereby you can see that same size should be compared. So, size has got some effect, this one must remember. Loading rate is the other factor. It seems it has been observed, as we shall see through some curves, that higher loading rate yields higher strength, higher loading rate yields higher strength, and this is related to criteria of failure. Now, I just would like to highlight what we mean by this. There is something called creep of concrete. Now, creep is a phenomena whereby you apply a load and keep the load constant, you find with time the deformation increases, In other words, I can show you something like this, that supposing you have loaded a beam specimen, let us say with uniform load only, and its deflection is initially something like this. With time you have not changed the load, but its deflection might go on increasing with time. That means, if I plot x axis time and this side the maximum deformation, let us say deflection, maximum deflection, I will find that possibly instantaneously it will show some deformation, and with time there will be some increase. So, this is nothing but elastic, this is elastic deformation, and this is creep, Okay, we may not have time to look into details of creep, but this is the creep deformation. So, this happens in case of concrete creep. That means, with time, even though you have not increased the load, its deflection increases in case of a beam, strain increases in case of a loaded cube specimen, you will find you just keep the load. So, initially it might have just deformed this much, but this deformation will go on increasing with time. So, deformation increases with time, and this phenomena is known as creep. Actually, I can quickly, since we are not looking into details of this, quickly I can give you an analogy. We can give you an analogy. Creep is something similar to consolidation of clay. Clay takes very long time to consolidate, same thing, something similar, much lesser effect of course in case of creep. The gel, water, etc., they are redistributed and thereby results in deformation or deflection, time dependent deflection, which although you have not increased the load. So, when you have increased the rate of loading, actually very quickly you have applied the load at a very fast rate, therefore, the effect of creep would not be there. But if you apply the load at a slow rate, very slow rate, then what will happen? The load is sustained for certain period of time, and therefore, there will be creep effect. So, this will result in additional strain in the material, and this has been attributed to lower strength at slower rate of loading. So, when you have higher rate of loading, you find the apparent strength is higher, whereas smaller rate of loading apparent strength is lower, and this because as I mentioned, the strain criteria for failure, which tensile strain criteria for failure, which can be thought to be about 100 to 200 micro strain, right, this being constant under a slow rate of loading, actually the strain will be reached at lower load, and therefore, it will fail early. Ultimate strain will be reached at lower load, and this will fail early. So, this is what has been observed, and let us see how is the variation that has been observed. So, large number of specimen when tested, you can test with strain controlled machine, servo controlled machine, control the strain rate. Most of our machine of course are we can control the rate of loading. Not necessarily all cube testing machines can have rate control. Sometimes it is controlled manually, but they can give you erroneous result, because the rate of loading is an important aspect of strength measurement of concrete. So, one has to maintain the specified rate of loading, which has been standardized by the code. I will come to that, but some machines can control the strain rate, and when this was measured with the strain rate control machine, now strain rate per second, you see this is 10 to the power minus 8, right, and minus 6, etc., etc. So, as you go on increasing the strain rate of application of strain per second, the strength goes on increasing. So, measured strength to the static strength. So, the static strengths are measured at this kind of strength, as you can see at this something like roughly about 10 to the power minus 5 strain per second. So, 10 micro strain per second, at that kind of rate of loading normally we apply. So, when you increase the rate of loading or reduce the rate of loading, you see if you increase the rate of loading at 10 to the power 2 10 to the power 2 strain per second, you can have a strength as much as twice of that one, twice of that what you find at normal condition, right. This is strain rate of loading. If we look at stress rate of loading, similar sort of situation we will see, and this is what is the stress load of loading, and it shows that it again increases exponentially. This is of course in pounds per second, rate of loading pounds per second. So, relative strength increases actually exponentially, but this aspect is important in testing, and this parameter must be taken care of in testing of concrete, in laboratory quality control testing of concrete. In fact, all those aspects we have mentioned, they are important while laboratory testing of concrete. It has been actually, it is suggested in IS 516 140 kg per centimeter square per minute, which is 14 MPa per minute for cube. This rate has been suggested for cubes, this rate has been suggested for cubes, this is the rate suggested for cube, and for cylinders this is the rate suggested 12 MPa per minute. So, the machine must apply the load at this rate, machine must apply, and it must be a machine capable of controlling the rate of loading. If it is not capable of controlling the loading and it is being done manually, well, this may result in some sort of error in the measurement. But even very old machines are are capable of controlling this rate. Cube compression testing machine are capable of controlling rate. Only thing, they should not be manual. Even mechanical devices, they are capable of controlling the rate. So, 14 MPa per minute is the Indian standard, or even it is there elsewhere also, and when it is cylinder, it is somewhat slightly smaller, 12 MPa per minute. So, this must be remembered while testing concrete for cube strength, testing concrete for cube strength. The next factor which is important for test conditions are moisture condition. It has been observed that moist specimen shows lower compressive strength than dry specimen. It is interesting. In case of compressive strength, the lower moist specimen shows lower strength, whereas it has been observed if you are testing the specimen under tension, which we shall discuss later on, in case of tensile strength testing, it is other way around. Dry specimen shows actually lower strength compared to moist specimen, but in case of compression test, moist specimen shows lower compressive strength than dry specimen. We will explain the reason, all right, but before that one must understand that why therefore code actually specifies the moisture condition, that you got to take it out not too much earlier before testing. You must take it out, there is a time specified, and preferably it should be tested immediately on removal from water. You can make it surface dry, right. ASTM actually specifies this. Now, what happens, why does it so, why it is so? The lowering of strength due to drying in case of tensile strength has been attributed to drying shrinkage. So, if you dry the specimen, the new shrinkage cracks will come. So, when you are trying to test it under tension, it gets lowered, but that is as far as tension is concerned. In compression, the behavior is other way around. So, what is the explanation? Well, the explanation was given is something like this. The explanation that has been suggested is something like this. You have more adsorbed water now, and this causes dilation of the cement gel. That means cement gels get separated, they are spreaded now, they are spreaded now because the adsorbed water goes between them and therefore they can push them apart. If you withdraw the water, they come closer, and shrinkage, drying shrinkage is because of that. In fact, when collapse of the gel layers takes place, that could be shrinkage. Now, when you have water and lot of adsorbed water is there, this essentially means that gel water will push the layers away and there is a kind of dilation. Now, this dilation results in lower cohesion between the gel particles or gel layer, and since there is lower cohesion, lower cohesive force, so there will be lowering of the strength. But the fact remains that the cube shall be tested, the moist cube shows lower strength. So, this also needs to be standardized, and therefore, the code tells you that it should be tested on removal from water. The immediately after removal from water, you should test this. You should test this as quickly as possible. So, I think these are the test factors. Now, few issue becomes important. The compressive strength, we have discussed what are the factor, how do we measure the compressive strength. Now, we have seen that we can measure it on specimen, and again let me reiterate, which I have stated earlier also, that this measured strength is quite different from the strength in the structure. It depends upon obviously the mixed parameters, all right, mixed parameters, casting and curing of the specimens, but depends strongly on the test parameters as well. Therefore, this test can be at best an indicator of the strength in the structure and correlated, and but can be very usefully very effectively used for quality control purposes to find out that strength potential of the mix. So, that is the first issue. So, we have seen that we can measure through cylinder as well as cube, although the Indian standard uses 15 centimeter cube. And then we have also seen that various test factors, namely end capping, H by D ratio, size and rate of loading, moisture condition, all this affect. Just repeating the same thing, capping, H by D ratio, these two factors are mainly because of what is called Platon effect, or because of the effect of the lateral, lateral movement, because of restrainment of the or restriction to lateral movement. This is because of the restriction to lateral movement. So, a capping which will restrict the lateral movement would actually show you a higher apparent strength compared to a capping which does not restrict the lateral movement. The machine plate does this effect, and this effect is limited to about 0.6 into the dimension of the specimen. Thereby, in case of cube it is overlapping, in case of cylinder which has got H by D ratio more than 1.7, this is some portion is there at the center where there is no effect, and therefore, cylinder fails at lower load. And we understand that it is about 80% apparent strength that you get in case of cylinder is 80% of that of the cube on an average, although it is a function of the strength. Similarly, this effect of H by D ratio is also a function of the strength, but for our general understanding, we just we of course, we do not take a value or anything of that kind, but we understand that higher nu by E and lower nu by E of the capping material will have some effect on the strength of the concrete. Rate of loading is the other issue, and this is important issue because rate of loading, while doing quality control in the quality control laboratory, one must control the rate of loading. We have seen that if you increase the rate of loading, the strength can be even double, but that is very high rate of loading, and at small rate of loading, of course, at small rate of a slow rate of loading, the failure can be at the lower load, and this has been attributed to the phenomena of creep in case of concrete. The last aspect that we looked into was the moisture condition, and we have said that it is dilation of the gel system because of adsorbed water, which reduces down the cohesion. It actually brings down the strength of the concrete. So, moist specimen shows lower strength compared to dry specimen, in case of cube compressive strength. All this points out to one thing, that cube test or cylinder strength results that we get is simply a relative measure of the strength potential of the mix. It is a relative measure of the strength potential of the mix. It can be correlated to the strength of the structure, but you have a good high Q strength high Q strength may have a good strength in the structure or may not be. That is a separate issue that will depend upon the compaction and curing etc. condition at the site itself. But cube, when done in a standard manner, we have standardized, we have seen that all other things are standardized. Moisture condition has been standardized, rate of loading has been standardized to 140 kg per centimeter square per minute or 14 MPa per minute. The capping condition or platen condition in case of cube has been standardized with plane surfaces remaining in contact with the cube. Rate of loading has been standardized. So, when all other things have been standardized, the cube strength gives you a relative measure of the strength of the concrete. This is important because that is why this is being repeated, that it is only a relative strength potential of the relative measure of the strength potential of the mix. Nevertheless, this is the one, this is how we do quality control, this is how we do all quality control, and this measure that we take, this value is used also in design because we can correlate this to the actual strength in the structure, and in design we take a value of 1.5. We assume that Q strength is about 67% of that of the strength in the structure, actual strength will vary. So, these are the compressive issues related to compressive strength. We can next time we can look into the other aspects of concrete strength, namely tensile strength etc. and modulus of elasticity. Okay. So, this we can conclude this lecture.